We live on a restless planet in a restless solar system, within a restless galaxy. You know Earth spins on its axis and orbits our sun. That sun, our star, isn't stationary either. It journeys around the center of our Milky Way galaxy, taking over 200 million years to complete a single lap. But the story of cosmic motion doesn't end there, not by a long shot. Our entire Milky Way galaxy, a magnificent spiral of hundreds of billions of stars, is itself hurtling through the vastness of intergalactic space. This isn't a random drift, it's a directed voyage, a grand cosmic pilgrimage towards an unseen, powerful influence. There's something out there, a cosmic heavyweight, pulling us, and much of our galactic neighborhood, towards it. This great cosmic mystery beckons us to ask, what is this powerful force? So what is this enigmatic cosmic entity? We call it the Great Attractor. Now don't picture a single gargantuan black hole or one colossal star. The Great Attractor isn't one discrete object you can point a telescope at and say, there it is. Instead, imagine a vast, sprawling region in space, an enormous concentration of mass, and therefore an immense gravitational pull. It's more like a huge invisible dip or valley in the fabric of space-time, drawing matter towards its center. Its true nature has been shrouded in mystery for decades, partly because it's so hard to see directly, hidden behind the clutter of our own galaxy. It's a cosmic enigma, a gravitational giant playing hide-and-seek with our best instruments, challenging our understanding of the universe's structure. Why should we care about this distant, diffuse giant? The Great Attractor is profoundly important. Its gravitational influence isn't just a minor tug, it affects the motion of hundreds of thousands of galaxies, including our very own Milky Way, across a region of space hundreds of millions of light-years wide. Think about that. An entire section of the universe, a supercluster's worth of galaxies, is feeling its pull. Understanding the Great Attractor is crucial for comprehending the large-scale structure of the cosmos. It helps us map how galaxies cluster together, how these massive structures formed after the Big Bang, and it gives us vital clues about the distribution of matter. Not just the luminous stars and gas we can see, but also the invisible, yet gravitationally dominant, dark matter. Let's try an analogy to grasp its scale and effect. Imagine you're on a tiny raft in the middle of a colossal dark ocean. You notice that your raft, along with countless other rafts scattered as far as you can see, is slowly but surely drifting in a specific direction. You can't see any land, no obvious source for this movement, just the steady, inexorable pull. That's precisely what our Milky Way and its neighboring galaxies are experiencing. The Great Attractor is that unseen, powerful current in the cosmic ocean, a deep, gravitational well, shaping the flow of galactic traffic across an unimaginable expanse. It's a silent conductor orchestrating a grand cosmic ballet, and we are all part of the dance. So where in the vast cosmic expanse is this Great Attractor hiding? It lies in the direction of the southern sky, towards the constellations Hydra and Centaurus. If you could travel there, you'd be undertaking a journey of roughly 150 to 250 million light-years. That's an almost incomprehensible distance. Light from the Great Attractor region, traveling at the ultimate cosmic speed limit, takes hundreds of millions of years to reach us. This region of space is already known to be densely populated with galaxies, forming part of what astronomers call the Hydra-Centaurus supercluster. The Great Attractor itself is understood to be a particularly dense concentration of mass, a gravitational focal point, within this already crowded cosmic neighborhood, or perhaps even beyond it. One of the biggest challenges in pinpointing and studying the Great Attractor is something astronomers call the zone of avoidance, or sometimes the zone of obscuration. This isn't a dangerous cosmic minefield, but rather a band across our sky that is heavily obscured by the contents of our own Milky Way galaxy. Imagine trying to look at a distant city skyline, but there's a thick, dusty, brightly lit fog bank right in front of your eyes. Our galaxy's disk, filled with stars, gas, and vast clouds of interstellar dust, acts like that fog bank, blocking the light from objects lying directly behind it in that plane. The Great Attractor, unfortunately, happens to be located right behind this galactic curtain. How did scientists even begin to suspect its existence if it's so hard to see? The first clues emerged in the 1970s. Astronomers were meticulously charting the motions of galaxies. According to the prevailing understanding of the expanding universe, most galaxies should be receding from us, with their speed proportional to their distance, a concept known as Hubble's law. However, careful observations revealed something peculiar. Galaxies in a large volume of space, including our own local group, weren't just moving away smoothly with this cosmic expansion. They showed an additional shared motion, a peculiar velocity, all directed towards the same general area of the sky. This was a clear sign that something massive and unseen was exerting an extra gravitational pull. This initial detective work relied on clever techniques. Scientists examined the cosmic microwave background, CMB, the faint afterglow of the Big Bang that permeates all of space. They discovered a slight variation in its temperature across the sky, a phenomenon called the CMB dipole. One side of the sky appears infinitesimally warmer, and the opposite side infinitesimally cooler. This dipole is interpreted as the result of our solar system, and indeed our entire local group of galaxies moving at a significant speed relative to the CMB reference frame. This bulk flow of galaxies, this collective drift, was a crucial piece of evidence pointing towards a powerful, distant gravitational source. The Great Attractor was starting to reveal its presence, not by what we could see of it, but by how it moved us. Let's talk about the sheer gravitational muscle of the Great Attractor. Its influence on our own Milky Way galaxy is profound. We, along with our galactic twin, the Andromeda Galaxy, and the dozens of smaller galaxies that make up our local group, are not just idly drifting. We are being pulled inexorably towards this massive cosmic entity. The speed of this journey is astounding, around 600 kilometers per second. That translates to over 2.1 million kilometers per hour, or about 1.3 million miles per hour. Imagine covering the distance between New York and Los Angeles in about 7 seconds. That's the kind of cosmic hurry we're in, all thanks to the Great Attractor's invisible hand. And it's not just our local galactic family that's caught in this cosmic current. The gravitational reach of the Great Attractor extends much further. The Virgo supercluster, a colossal assembly of thousands of galaxies, of which our local group is just a tiny outlying member, is also part of this grand inflow. Even larger structures, encompassing vast swaths of the nearby universe, feel this dominant pull. This indicates that the mass responsible for this attraction must be truly enormous, far exceeding the combined mass of all the visible stars and galaxies we can observe in that direction. It points to a concentration of matter with the gravitational equivalent of tens of quadrillions of suns. When the Great Attractor was first proposed, astronomers wondered what could possibly possess such immense gravitational power. The leading hypothesis was that it must be an incredibly massive, unobserved supercluster of galaxies lurking behind the obscuring veil of the Milky Way's zone of avoidance. The challenge was to find this hidden giant. If it were composed of ordinary matter, like stars and gas, it would have to be an exceptionally dense and extensive collection of galaxies. The estimated mass required was staggering, something like tens of thousands of times the mass of our entire Milky Way galaxy, all concentrated in that one region of space. Over time, and with more sophisticated observations, our understanding has evolved. While the Great Attractor region is indeed rich in galaxies, the picture is more nuanced. In 2014, astronomers defined an even larger structure, a supercluster called Laniakea, which means immense heaven in Hawaiian. Laniakea is a colossal cosmic web, and our Milky Way is part of it. The Great Attractor is now understood to be a major gravitational focal point, like a large valley or basin within this Laniakea supercluster. Galaxies within Laniakea, including ours, are flowing towards this central region. So the Great Attractor isn't necessarily a single discrete object, but rather the dominant gravitational center of our home supercluster, a vast concentration of both visible and dark matter. So, how do we study something that's playing such an effective game of cosmic hide-and-seek behind our galaxy's dusty curtain? While optical telescopes, which see visible light, struggle with the zone of avoidance, astronomers have other tools in their cosmic toolkit. Different wavelengths of light can penetrate gas and dust much more effectively. For instance, X-ray telescopes can detect the extremely hot gas that permeates clusters of galaxies, gas that emits strongly in X-rays. Radio waves, too, are much less affected by interstellar dust, allowing radio telescopes to map the distribution of hydrogen gas, a key component of galaxies, even when they are hidden from optical view. Scientists are actively using these alternative cosmic eyes to chart the territory of the Great Attractor. Surveys like the Parkes HI Zone of Avoidance Survey, utilizing powerful radio telescopes in Australia, have been systematically scanning the obscured region, detecting the faint radio signals from hydrogen in distant galaxies. X-ray observatories orbiting above Earth's atmosphere, such as NASA's Chandra X-ray Observatory and ESA's XMM Newton, have also contributed by identifying galaxy clusters in that direction through their X-ray emissions. It's like a painstaking archaeological dig, slowly uncovering the hidden structures piece by piece, galaxy by galaxy, to reveal the true nature of this gravitational behemoth. Why is this quest to understand the Great Attractor so critical? It's about more than just mapping one interesting region of space. The Great Attractor serves as a crucial laboratory for testing our fundamental theories of cosmology and gravity on the largest scales imaginable. Its immense mass and influence provide vital insights into the distribution of matter in the universe, particularly the mysterious dark matter. Dark matter doesn't shine or reflect light, but its gravitational pull is undeniable, and it's thought to constitute the vast majority of matter in the cosmos. The Great Attractor's pull is largely due to this unseen dark matter, so studying it helps us understand this elusive substance. The Great Attractor, therefore, remains a captivating frontier in astronomical research. It reminds us that the universe is not a static, unchanging backdrop, but a dynamic, interconnected system of immense structures, constantly evolving under the influence of gravity. Each new observation, each refined measurement, brings us a step closer to fully comprehending this cosmic giant, and by extension our own place within the grand, flowing currents of the cosmos. It's a testament to human ingenuity and our unyielding curiosity to explore the unknown, to push the boundaries of our knowledge, and to truly grasp the magnificent scale and complexity of the universe we inhabit. The journey to understand the Great Attractor is far from over.